we're focusing on measurement and data and geometry since they're pretty close related. Let's take a moment to go over the measurement and data cluster here. There is a lot going on. I'm not going to read it all because we're going to go through the majority of the different types of problems at these in case within the next few slides. So take a moment to read through them. There is a lot here, but if you've probably noticed at this point by going through standards, there are many questions or problems that we bring up or discussion that we talk about, and it covers more than one specific standard. It crosses them. So keep that in mind, that although there's a bunch of individual ones, there are many things that we can do to help students that cross-relate one another together. Further, cross-relates more than just one cluster. So it might cross-relate measurement and data with geometry, or geometry might go in with operations and base 10. So keep that in mind as we go through these. The Robotics Club is having a robot race. They raced 4 of their favorite robots to see how fast they can move. The race started at 12:55 p.m. The times on the chart show how long it took each one to reach the finish line. Find the time each robot finished so it can be written on the trophy. So it looks like the pink robot finished in 16 minutes, the orange robot in 21 minutes, the blue robot in 12, and the green robot in 27 minutes. Some questions to think about, something that you might ask your students or you may be thinking about yourself. What is the task asking us to do? What information do we have? Do we need more information? Is there more than one solution? Can you explain your solution? How can you tell which robot was first? What strategies and tools can you use to show the finish times? How can we use a number line to complete this task? So the race started at 12:55 p.m. So I have a number line here, and notice that I start my number line right here at 12:55. And then I've got a red benchmark of 1 o'clock. And notice that it is broken into smaller benchmarks of 5 minutes in between. So let's start with the pink. They finished in 16 minutes. So if they started at 12:55, we could jump 5 minutes to 1, 5 minutes after 1, 10 minutes. So we've gone 5, 10, 15, one more to make 16. So I see on my number line that that equates to 1:11 p.m. When I look at the orange robot, I can just go off of where I just finished with my pink one. If I went 5 more to get 5, 10, 15, 20 minutes, then I just need 1 more minute to reach 1:16. The blue robot, however, finished in 12 minutes. So we would need to go 5, 10, plus 2 more to get 12. So this would be 1:07 p.m. The green robot finished in 27 minutes. So we need to count by 5s, 5 minutes, 10, 15, 20, 25, 26, 27 for 1:22 p.m. Why would we begin counting by 5s instead of 1s? If you think about that for a minute, it makes more sense because we have a long distance to go, and it's easy to count by 5s on the clock. We certainly could count by 1s, but it would take us a while. And sometimes we don't necessarily want the quickest way, but the way that makes the most sense. And did you notice any patterns as you were going along? This activity shows us that time can be measured, and that time represents the duration of an event from its beginning to its end, no matter what time it starts. The robot race trophies are ready to be awarded. Each one should show the fastest finish time from a race that color robot won. Write the time from the number line on the clock on each trophy. Explain how you determine the times on the number line. Take a moment, pause the video, complete this activity, come back, and let's talk about it. Okay, I got 3:37 p.m. from the number line below above. I see that we have the 3 o'clock benchmark. I see that we are past the smaller benchmark of 35 and I go 2 more spaces to get to 37. For the gold one, I see 4:14 p.m. So I see the 4 o'clock benchmark. I can go the 5-minute, 10-minute benchmark and then 4 smaller spaces plus 4 more to get to 4:14. And finally, the pink one, I get 4:49. I'm still slightly past the 4 o'clock, but not quite to the 5 o'clock benchmark. I am past 4:45, but not quite to 4:50. So I count 1, 2, 3, 4 to get 4:49. It usually takes Erica 45 minutes to do her homework. If she starts her homework at 5:30 p.m., what time will she finish? One day, Derica started her homework at 6:45 p.m. and finished her homework at 7:20 p.m. How long did Derica spend on her homework? Another day, Derica finished her homework at 5:05 p.m. after spending 40 minutes on her homework. What time did Derica start her homework? Work through these elapsed time problems using an open number line. Pause the video, see what you can do, and come back and we'll talk about each one individually. So when I look at the first one, it takes Derica 45 minutes to do her homework. She started her homework at 5:30 p.m. So I start my open number line. Recall that an open number line doesn't have tick marks pre-listed. We create them as we need them to kind of keep track of where we're going. So to get from 5:30 to 6 o'clock, a benchmark, I need to add 30. But I haven't quite elapsed 45 minutes. I still need 15 more minutes. So if I go from 6 o'clock, 15 more minutes would bring me to 6:15. 30 and 15 gives me 45 minutes. Therefore, Derica will finish her homework at 6:15 p.m. One day, Derica started her homework at 6:45, and you can see that I have a typo here. Here we go, fixed it. There we go. Started her homework at 6:45 p.m. and finished her homework at 7:20. How long did she spend on her homework? So to get from 6:45 to the benchmark of 7 o'clock, that's 15 minutes. But we still need to go to 7:20 because that's what time she finished. So we need another 20 minutes to get to 7:20. So overall, when I count how many minutes have elapsed, 15 plus 20 gives us 35. So Derica spent 35 minutes on her homework. So another day, Derica finished her homework at 5:05. After spending 40 minutes on her homework, when did she start? So remember, it's elapsed time. So we finished at 5:05. So we need to work our way backwards to find out when we actually started. So from 5:05 to our 5 o'clock benchmark, we subtract 5 minutes. But we need to spend 40 minutes. So we've only done 5 minutes so far. The next benchmark would be 4:30, a nice benchmark. So 30 and 5 is only 35. We still need 5 more minutes. So if I subtract 5 more minutes from where I started, it should be 25, we get 4:25. Therefore, Derica started her homework at 4:25 p.m. Yummy Nut Company needs to weigh these items before mailing. Cashews are 396 grams, licorice is 503 grams, and almonds are 454 grams. Use base 10 pieces to find the correct total and to help explain your answer. Using one of our virtual math manipulatives, I put up a thousands, hundreds, tens, and ones chart. I've also included our base 10 pieces so we can put together, we need to find out how much total they all weigh together. So when I'm talking about in total weighing all together, that means we need to add them. So I know that cashews are 396. Cashews are 1, 2, 3, and 96. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I need 6 ones. 1, 2, 3, 4, 5, 6. Okay, licorice is 503, so I need 5. 1, 2, 3, 4, 5. I'm sorry, our work mat's getting kind of 0 10s and 3 1s. And we need 454 almonds. 1, 2, 3, 4, 5 10s, 2, 3, 4, 5, and 4 1s. 1, 2, 3, 3, 4. 1, 2, 3, 4. Okay. For the sake of cleaning this up a bit, typically would work our way from the ones column all the way to the thousands column in order to simplify, but I want to try to get rid of some of these hundreds here. So I'm going to count out 10 hundreds makes 1 1000, so one group of 1,000. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That cleans it up a little bit here for us. Oops. So there's 2 of them here. Okay. Even though, yeah, they're linked too. Okay, so now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 that I can exchange for a one group of 10 here. I don't have any more to do that again. So now I need to do the same with my 10s to make a group of 100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. So now I have one group of 1,000, 3 groups of 100, 5 groups of 10, and 3 ones, for a total of 1,353. So I have the same question here, except this time let's use a number line to find the correct total and to help explain our answer. Deconstructing numbers will help us to add more accurately and more quickly on a number line since we don't have individually. I can see that they're also going by groups of 100, so 0 grams, 100, 200, 300, 400, 500, 600, 700, 800, 900, and 1,000. I can rewrite 396 as 300 plus 96, 503, which is 500 plus 3, and 454 as 400 plus 54. So notice I separated the hundreds group from the tens and ones, and I'll show you why here in a moment. In the last video, we deconstructed our numbers, and now we're actually going to go ahead and put them on our number line. So what I did was took the hundreds numbers and gathered them together and then grouped the tens and the one numbers off to the side. I can see that 96 plus 3 plus 54, I could build to another 100. So 96 plus 3 is 99. So if I borrowed one from 54, I would get 153. So now I can put these nice hundreds on our number chart. So I start at 0, I add 300, I add 500, 400, 100, and then the 53. So all together then, we have 1,353 grams, just as our base 10 pieces showed us. Further, number lines can help add, subtract grams, kilograms, and any other metric system number as well. Michael started hiking at the 2nd mile marker from a cabin. The number line shows the distance he hiked. How far did Michael hike that day? Well, if he started at the mile marker 2 and ended at 7, he went 1, 2, 3, 4, 5 miles. Michael and Helen were partners for a relay race. Helen ran 3/4 of a mile. The number line shows the distance that Michael ran in miles. Michael says he ran further than Helen since he ended up a mile away. Helen says they ran the same distance. Who do you agree with? Explain to the other person why they are wrong. Let's first identify what Helen did. Helen ran 3/4 of a mile. I can see that from 0 to 1 mile, I have 1, 2, 3, 4 parts before I get to a mile. So each part is equal to 1/4 of a mile. 1/4, 2/4, 3/4, 1. I see that Helen ran 3/4 of a mile. So let's say she started at 0, 1/4, 2/4, 3/4. I can see that if I were to move Helen's bar over to Michael, that he also ran 3/4 of a mile. So even though he ended up at a further distance, he ran the same distance because he started a bit further than Helen did. We can measure distance at varying points on a ruler or number line, and the length does not change. No matter where we start, the length will stay the same. A constant length between the starting and ending points of an object on a ruler or number line can be expressed in many different ways. Oliver and Michael are reporting the distances they hiked to their PE teacher for extra credit. The number line shows their distances. How far did each student hike? Again, I see that each mile is broke into 1/4, 2/4, 3/4. So I can see that, let's say this is Oliver here. He went 1/4, 2/4, 3/4, 4/4, 5/4, 6/4 a mile. And if I bring these arrows down here to look at Michael, he went the exact same distance as Oliver, even though he started at a different location. So each student hiked 6/4 of a mile. Itty Bitty the ladybug is training for the insectathon. Every day she takes a rundown ruler road. She gets bored easily, so she never starts or ends in the same place. While showing her friends the table she made to track her distance, Itty Bitty spilled her coffee and some of the numbers were smudged. Can you help her determine what the missing numbers were? So I have a ruler down here for us, and I have our chart. So we're going to start with Monday. So recall that the first column is start, the middle is end, and the last is total. So on Monday, we start at 1/4. We don't know where we end, but we know that we went a distance of 5/4. So we started at 1/4. So we need to go to the part where our number line is broke down into equal parts of 4. So 1/4, 2/4, 3/4, 4/4. So we start at 1/4, so I have an arrow where we start, and we went a distance of 5/4. So 1/4, 2/4, 3/4, 4/4, 5/4. I see that we end at 6/4 on Monday. On Tuesday, we start at 2/8 and we end at 5/8. We want to know how far we traveled. So the in-between marks, these little ones, see that they split our 1 inch into eighths. So we start at 2/8, which should be here. Let's try that again. So she starts at 2/8 and she ends at a total of 5/8. 1, 2, 3, 4, 5/8. How far did we go? So we can count. We went 1/8, 2/8, 3/8. So she went a total of 3/8 distance on Tuesday. Go ahead and finish the remaining questions on your own and we'll come back together. Wednesday she ended at 11/2. Thursday she ended at 7/4. Friday you get to choose. Hopefully you chose something fun. Brock is building the perimeter of his sandbox. He has 3 boards that are 12 feet long each. The area of the sandbox is going to be 48 square feet. Explain whether or not you think you will have enough board length to build the perimeter. We have 3 boards that are each 12 feet long for a total of 36 feet of boards. So 3 times 12 is 36. So some possible options for the dimensions of our sandbox would be 1 by 48. So to find the perimeter, we add all of our outsides together. 1 plus 1 plus 48 plus 48 is 72 feet. 2 feet by 24 feet. So 2 feet plus 2 feet plus 24 plus 24 is 52. We could do a 13-foot by 16-foot or a 6-foot by 8-foot, giving the possible perimeters. I only have 36 feet of board though, so I could not do a 1 foot by 48 feet because 72 is greater than 36. I also could not do a 2 foot by 24 foot because 52 feet is still greater than 36. 3 feet by 16 feet is getting closer, but still too many. It looks like we have 6 feet by 8 feet to get us a total of 28 feet of boards. Would have to be the dimensions of our sandbox. Find the area of each colored figure if each square is 1 square inch. Well, if each little box is 1 square inch, then I can simply count them. I have 1, 2, 3, 4, 5 square boxes filled in that are full. So the area is 5 square inches. Here I have only 4 that are full squares and I have some half squares, but I can combine them together. I can combine the 2 half squares on the left to give me 5 and the 2 half squares on the right to give me 6. The area is 6 square inches. Brock, Reba, and Van are comparing the sizes of their sandboxes. They each think that their sandbox is the largest. Determine the volume of each sandbox to compare and decide whose sandbox has the largest volume. Brock's area of his sandbox is 48 square feet, but a height of 12 inches. Reba's area is 18 square feet. Her height is 3 times as big as Brock. And Van's area is 24 square feet, but his is double the height of Brock's. So recall that the product of the area of the base and the height of the right rectangular prism is equal to the volume. They're equivalent formulas that we can use to calculate the volume of a right rectangular prism. Length times width times height is equal to base times height, where base is the area of our base. And I'm given you the area of each Brock, Reba, and Van. So Brock's volume is the area times its height. So his area is 48 square feet by 1 feet because 12 inches is equivalent to 1 foot. If we did 12 inches, we would get a number that is significantly higher. So it's important for students and for you to remember that we have to convert from feet to inches or inches to feet, whichever way, keep it the same throughout so that we can compare apples to apples, inches to inches, those kinds of things. So 48 times 1 is 48 cubic feet, which is Brock's volume. Reba's is 3 times as tall as Brock. So whatever height Brock had, which is 1 foot, Reba is 3 times as many. So her area is 18 square feet times her height is 3 feet, which is 54 cubic feet. And finally, Van is 24 square feet, and his height is double Brock's height. So double 1 foot is 2 feet. So 24 square feet times 2 feet is 48 cubic feet. When I compare their totals together, I see that Reba has the largest volume and Brock and Van are equivalent. So Reba has the largest volume. How many circles are there in all? Write down a number sentence that represents the total. Pause the video and take a moment to do this. We'll come back and talk about some possibilities. So you could have 3 times 8. So 3 times 8. You could have 4 times 6, which is half of 8 and double 3. You could have 8 plus 8 plus 8, or 3 plus 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 3, like we learned in 2nd grade. Alfonso said he figured out how many shaded circles there were first, and then how many unshaded circles there were second. Once he knew how many of each, he added them together to find the total. Write a number sentence Alfonso could have used that shows his reasoning. So when I look at the shaded portion, I have a 3 by 6, and I have a 3 by 2 for the unshaded portion. Multiplying them together and adding their result gives us a total of 24. So he took the unshaded plus the shaded. Jennifer said, I just saw 3 rows of 8 circles. Write a number sentence that Jennifer could have used that shows her reasoning. Her reasoning is 3 rows of 8. 3 times 8 is 24. The area model below shows the floor plan for a storage closet. The storage closet will have a tiled floor with gray tiles on the left and white tiles on the right. How many tiles are needed for the storage closet in all? Write down a number sentence that shows how you thought about it. Pause the video and we'll come back and talk about possible solutions. Let's talk about some possible number sentences that you may have gotten in the last video. 5 times 7 is 35. 10 plus 10 plus 10 plus 5, which would be going off of the 10 frames, a group of 10, a group of 10, and 5 more. 5 plus 5 plus 5 plus 5 plus 5 is 35, etc. Think back to how Alfonso figured out how many circles there were. Use Alfonso's same strategy here to find out how many tiles are needed. Write a number sentence with Alfonso's reasoning. Think back to how Jennifer figured out how many circles there were. Use Jennifer's same strategy here to find out how many tiles are needed. Write a number sense with Jennifer's reasoning. Pause the video, see if you can flip back, take a stab at it, and then we'll reveal the answer. So Alfonso found 25 shaded tiles and 10 white tiles, so 35 tiles in all. So he did 5 by 5 for the shaded, and he did a 5 by 2 for the unshaded, and got total of 35. Whereas Jennifer found the total of 35 tiles in all by taking a 5 by 7. What is the greatest area you can make with a rectangle that has a perimeter of 24 units? What are the possible dimensions of a rectangle that has a perimeter of 24 units? And how can we determine their area? Take a moment, pause, jot some ideas down, and then we'll come back together. One possibility would be 8 plus 8 plus 4 plus 4 to get 24 units for our perimeter, and that the area would be 8 by 4, so 32 square units. We could also do a 10 by 2, so 10 plus 10 plus 2 plus 2 is 24 units for our perimeter, and our area would be 10 by 2, which is 20 square units. This one is much smaller than the first one, so far we do have a larger one, but is it the largest possible? We could have done 1 plus 1 plus 11 plus 11 for 24 units, which would be a 1 by 11. Man, we're getting smaller. This is only 11 square units. We could do a 6 by 6, which is 6 plus 6 plus 6 plus 6, which is 24 units. And the area would be a 6 by 6, so 36 square units. When I compare all the square unit options, I see that this is the largest. So a square gives us the greatest area in this particular instance. Geometry. This one is very much smaller than measurement and data, but equally as important as we continue to talk about shapes and their attributes and partitioning those shapes. For each of the pictures, explain how you can see that half of the square is shaded. Take a moment to see if you can't figure this out on your own by pausing the video. Let's look at the first one. I see that if I were to cut my square in half, I'd have 2 rectangles. I also notice that if I were to cut the diagonals in half, that exactly half of each rectangle is shaded. So therefore, half of the square is shaded. Moving to the middle one, if I cross-cut vertically and horizontally straight down the middle, I see that exactly half of each partitioned area is shaded, so therefore the whole thing would have to be half shaded. The last one's a little more tricky, but if I cut down my center or fold in my center, one idea would be to see that if I were to take the circles and cut out the black circle and the white circle and interchange them, they would be the exact same size, so I would have half black and half white, so therefore half is shaded. For each of the pictures, decide whether one half of the circle is shaded or not. Explain how you know. Again, pause the video, take a stab at this, and see how you do. Looking at the first circle, if I were to cut down the middle, I would be able to take that black triangle that's kind of cut off there, and I would be able to easily fit it into this open white area, so therefore exactly half is covered. However, the second one, if I were to imagine moving these 2 unshaded pieces together, I can see that they're not going to fill up half the circle. So therefore, more than half must be shaded. And that's great when we compare the third one, because notice that if we were to cut them vertically and horizontally, that there is exactly the same amount of shaded as unshaded,
Whereas these ones, the black parts are just a little bit more than these here. And then finally, the last one, the small shaded piece on the left is the same size as the unshaded piece on the right. So I imagine that these two pieces trade places, and therefore we would have equal amounts of shaded and unshaded. Next week, we are going to finish third grade. It has its own special week because we are finally going to introduce fractions and how to work with fractions. And I just feel that it's important we take a whole week on fractions. This is really where we develop a solid foundation of fractions, and they're important for students so that they're comfortable moving forward. So we'll see you next week.